Hello, I'm Mohamed Yoonus, currently an undergraduate student from Government Engineering College Idukki. So here we are going to study about the topic mathematical analysis, constellation diagram and probability of error for Bfsk. So before studying these three things, we need to know what is Bfsk, right? So let's look. Okay, BFSK stands for what? Binary frequency shift key. So BFSK, the abbreviation stands for binary frequency shift key. So the most common type of FSK is binary FSK. So B stands for binary. So what does binary means? We all know binary means ones and zeros. Okay, so usually one means high and zero means what? Low, right? So BFSK is a form of low performance, a form of digital communication. We all know we are studying BFSK in DC, in digital communication theory, right? So it is what? It is a form of low performance form of digital communication. So it has only two inputs. As we said earlier, we said that binary means it will be having two inputs, right? So what are they? Ones and zeros, right? Okay, so it will be having two inputs. So where will we give this input? That's the question, right? With BFSK, the sender or carrier frequency is shifted by the binary input signal. Okay, so when we give this input signal, what are the input signal? Ones and zeros, the binary input signal, the sender or carrier frequency, okay, it is getting what? It is getting shifted. That is what we need to understand. So consequently, the output from a FSK modulator will be a step function in frequency domain. In what domain? In frequency domain. So the output from a FSK modulator. Okay, the output from a FSK modulator will be a step function. Also, as binary signals changes from 0 to 1 and vice versa, the FSK output frequency will shift between two frequencies. Okay. So when the input signal changes from 0 to 1, so we know there are only two inputs here that are ones and zeros, as it is binary. So when it changes from 0 to 1, vice versa, 1 to 0, what happens to the output? The output frequency will shift between two frequency. Okay, maybe to high to low or low to high, like that. So can we call this as an oscillator? Yes, of course. Not in the as a sense of an electronic oscillator, right? But anything that varies its value between two specific interval can be called as what? An oscillator, right? So in that case we can call. Okay, so the last point is a mark or logic 1 frequency and a space and logic 0 frequency. So what are the two frequencies? Logic 1 and logic 0 frequencies. Okay, so here's a diagram. Here I have said earlier that 1 means high, right? 1 means high and 0 means what? Low. So we can write infinite kind of information with this 1 0 1 0 representation, right? Okay, so 1 means high and 0 means low. So there's nothing to worry about this picture actually. It is just show us what is actually BFSK is. Okay, so what happens when we give input? That's it. It may be 1 or 0. Okay, so just look here. When it is 1, it got what? A low frequency, but when it is 0, the frequency, that is the number of cycles per second, is increased. Okay, that's in just for study purpose. Okay, in FSK, the frequency of a carrier signal is shifted between two discrete value of frequency f1 and f2. Okay, so what does that mean? In FSK, the frequency of carrier signal is shifted between two discrete value of frequencies. So two discrete value frequency means what? F1 and f2. Where are they? Here it is, f1 and f2. So what happened to them? They just shifted. Okay, so here is accordingly it can be said that these S1 and S2 are what? They are signals. What kind of signal? Maybe sinusoidal signals. Okay, so what does this represent is that S1 function of t is equal to square root of 2 EB upon TB cos 2 pi f1t. Let's represent this as simple one. Also, s2 of t is equal to, or s2 function of t, s2 as a function of t is equal to square root of 2 upon tb cos 2 pi f2t. So what's the difference between these two signals? One is frequency f1 and another one is frequency of f2, right? So I'm giving this as simple 1 and this as simple 2. So when looking at these things, we have to know what do you mean by EB and TB, right? So what is TB? Here it is. TB is the simple duration, okay, simple duration, and EB is that it is the transmitted signal energy per bit. Okay, so there's a condition that we need to know, that is the frequency f1 and f2 must be equal to integral multiple of 1 upon TB. Okay, so the frequency f1 and f2, I have said earlier that it will what in the FSK the frequency of carrier signal is shifted between two discrete value frequencies, right? So the frequency, these f1 and f2 must be an integral of integral multiple of 1 upon TB. So f1 is equal to n1 by TB and f2 is equal to n2 by TB. So what will be f3? It will be f3 is equal to n3 by TB, right? So likewise we have to say that where n1 and n2 are integers, okay, so it may be some kind of 1 2 3 4 5 like numbers, right? So normally carrier frequency this fc is very much, that is this fc is very much greater than what f1 and f2, this f1 and f2. Okay, so how can we calculate f1? By n upon tb is equal to f1. Okay, so normally the carrier frequency fc is very much greater than f1 or f2. So the difference between f1 and f2 will be what? It will be very small. Okay, so okay, here we are going to look at the orthogonal state. Okay, so considering s1 of t and s2 of t, x2 function of t are orthogonal signal. So what are s1 and s2? They are signals, right? So the integral 0 to tb s1 function of t multiplied with s2 function of t. So these signal, when these signals are multiplied, multiplied, and when we find the integral, we will get 0 and eb. So when will we get 0? That's the question, right? So we will get 0 when 1 is not equal to 2. What does this 1 and 2 means? When this both signals are not same, that is what they meant. When the signals are not same, we will get 0. If the signals are same, we will get EB as the answer. Okay, or 1 in the case of what? Unit energy. That's it. Okay, so therefore FSK signal is expressed in terms of orthonormal basis function. So we can express FSK, that frequency shift key, can be expressed in terms of basis function. What kind of basis function? Orthonormal basis function. Okay, so let us consider phi1 of t is equal to root of 2 by tb cos 2 pi f1t, where the time period is 0 less than t less than or equal to tb. Otherwise it will be 0. Also phi 2 of t is equal to same, but there's only difference in the frequency, right? Okay, so we just look at this condition. So in orthonormal basis function, we will get something like this. How are we going to get something like this? Okay, FSK in terms of orthonormal basis function phi1 t and phi 2 t. Okay, so let's think. Simple one is represented by what is this? Sinusoidal signal of frequency f1 is equal to n1 by tb. Okay, f1 equal to n1 by tb. Symbol 0 is represented as no signal. So in this case, symbol 1 is represented as a sinusoidal signal of frequency f1. Okay, also in this case, symbol 0, that is in s2, signal s2, that is this sinusoidal signal s2 is here. Symbol 0 is represented by sinusoidal signal of frequency f2. Okay, so in this case symbol n1 has a sinusoidal signal. In this case symbol symbol 0 has what? A sinusoidal signal. So in this case S1, does symbol 0 has a signal? No, it is absolutely no. That is what written here. Symbol 0 has represented by, is not, has no sinusoidal signal. Okay, that's it. Okay, so this is a constellation diagram. So for understanding constellation diagram, we need to know about the orthogonality force that we have discussed earlier. So we have here two signals. Okay, what are they? One got coordinates square root of EB comma 0, one got coordinate of 0 comma square root of EB. So what does that mean? So this can be what? S1 and this can be S2, right? So what does that mean? We have two axes, phi 1 and phi 2. The x-axis is phi 2 and y-axis is phi 1. So phi 1 have an equation as what? We know that this is phi 1 of t and this is phi 2 of t. So in orthogonality, in constellation diagram, when this is the decision boundary. Okay, decision boundary. So this is the constellation diagram. So how this value, how does we get this value? Okay, that's the question. So we know that in x direction we know the signal having only root AB comma 0, so it might be here, and also in y axis this phi 1 it have to be like here. Okay, this is the message signal. Okay, so okay, here we gonna find what is decision region of binary FSK. So let R vector. I'm doing this presentation on a phone, so that's why I don't have the letter for the alphabet of R vector, so I'm just mentioning this with this. So R vector, let's consider R1 and R2. So what is R1? R1 is the integral from 0 to TB R of t phi 1 of t. Correspondingly, similarly, R2 is like the integral of R of 0 to TB or R of t phi 2 of t dt. So what's the difference? The difference is only in the phi 1 and phi 2. So what is R? Okay, so it's a projection of what? Phi 1 and phi 2. So let's consider this diagram. We know in constellation diagram that this is what? S2 and this is S1, right? So which means this might in this diagram when something comes in this area, which means this might be R1, right? Because we have phi 1 here, so phi 1 will be at R1 region. So when something comes in favor to this region, it will come across this point. Okay, this is the message point S1, and if something comes in this region, that is in the R2 region, let's consider this as in the R2 region. If something comes in this R2 region, it will come to into this message point S2. I have not written a message point S2, but I have written here message point S1. Similarly, there will be a region like message point S2 over here. So if anything comes over here in favor with R2, it will come across this, and if anything come here in favor with S1, it will come across here. So what happens when something comes in this diagonal? Okay, what's the peculiarity? What is the peculiarity of this diagonal? It is R1 is equal to R2. Okay, so that's the decision boundary line. Okay, so this when something comes across this, it will come to here, and if something comes across this, it will come to here. That's the thing. So this is all things that I have said earlier. R1 region all maps to S1. I have said that if something comes in this region, it comes to S1. S1 is here. If R2 region all maps to S2. That is in this. If something comes in this region, it will all maps to here. And if R1 and R2 is equal to is same, that is it will form what? It will be on that diagonal. Okay, it will be on this diagonal. Okay. So now let's look at the last topic, probability of error for binary FSK. So what is probability of error for binary FSK? So given S1 is transmitted, right? So which one is transmitted? Signal 1 is transmitted, and we have R1 is equal to root of EB plus N1. Also R2 is equal to N2. Okay, let's consider the condition R1 is less than R2 means what? Which means getting a decision in favor of symbol S2, the conditional probability of error given S1 is transmitted is. So we have transmitted here is what? S1. So the conditional probability of given S1 is probability E of S1, that is signal S1. E means what? E means the error. Okay, error at S1 is equal to P of R1 less than R2 is equal to P of root of EB plus N1 less than N2. So where did we get this equation? Okay, so that's the question, right? So we know the condition is R1 is less than R2. Okay, why is that? Because S1 is transmitted. So when in this condition we can replace R1 with what? With root EB plus N1. That is what we have done here. Square root of EB plus N1. Also R2 with what? N2. So let's consider random variable n equal to n minus n1 minus n2. Since n1 and n2 are quotients, also it is independent and identically distributed. What does that mean? IID, independent and identically distributed with what? With n1 comma n2 is an element of n of 0 comma n0 by 2. Also n is a Gaussian with n is an element n of 0 comma n0. Okay, so this is n naught. I don't have any kind of it's just look like no, but it is actually n naught here. Okay, so what is the probability here? The probability of when S1 transmitted is probability error of S1 transmitted is P of E, that is probability error of S1 is equal to P of n less than minus of square root of EB is equal to Q of E, that is root of EB upon N0. It is not N0, it is N0. Okay, so similarly by symmetry we get what? Here it is when S1 is transmitted, but when S2 is transmitted we will get the same result. Okay, in that case when S1 is transmitted it will be R1 less than R2, but when S2 is transmitted it will be like R1 is greater than S2. So we will get a same equation as we got here. Okay, so looking at this equation we can say that the two signals are equally likely to be transmitted. The average probability error for coherent binary FSK or BFSK is what? Is this equation. So what does that mean? P is equal to, that is probability error is equal to Q of square root of EB upon N0. So BFSK is having more probability of error. Okay, so that's another thing. Now we are going to the last topic of this section, that is BFSK transmitter. So let us know what is BFSK transmitter. Okay, so here we are giving some input signal. Okay, maybe 0 or 1, like square something like that. But okay, so when we are giving this input signal we will get what? If it is 1 here it will be 1, if it is 1 here it will be 0. Why? We are using an inverter here, right? So if the input is 0 the inverter will give the input output 1. If we giving in the input 1 the inverter will the output 0. Okay, also we are having here two frequencies, f1 of t and f2 of t. What are they? It is root of 2 by tb cos 2 pi f1 of t. Also similarly another frequency f2 of t is equal to square root of 2 by tb cos 2 pi f2 of t. Okay, so these are two frequencies. So when we give one here, one as the one as the input, we get 0 here, and we only get 1 here, so it gets just added. Similarly when we give 0 it will get 0 here and 1 here, and it will get added with this binary FSK, so it will just get transmitted. So where does it go? We have to get a receiver, right? So coherent BFK receiver, when the signal is received over here. Okay, so the signals are received here, and it is integral from 0 to TB, and R1, and this is it is written as X1 and X2, and it is same as our R1 and R2. What is R? It is a projection of phi 1 and phi 2, right? We have studied that earlier. So this is a decisive device. So what happens when R1 is greater than R2? Will get what? Will get 1. Okay, if R1 is less than R2, it will get what? 0. That's the thing. So this is what decisive device. Okay, so I think my presentation is very clear. I will just say everything once more to get much clear. So I have said what is BFK. BFSK is and it stands for, and it's property, and how we are giving the input. There are only two input, zeros and ones, and we have said about the sinusoidal signals S1 and S2T, and the difference in frequencies F1 and F2T. Also we have said about the different the property that is the frequency of F1 and F2 must be equal to the integral multiple of 1 upon TB. Okay, also this N1 of F1 is equal to N1 N1 upon TB, where N1 and N2 are integers. Also we have said the orthogonal property, that is considering orthogonality, we get E0 and EB. When will we get E0? When only when one is not, that is signals are not same, and if the signals are same we will get EB, and it will get 1 when it is unit energy. Also we know we get represented by, when it is represented by sinusoidal signal of frequency F1 is simple 1 and simple 0. Okay, also we have studied about the constellation diagram, and this is a decisive line. Okay, this is boundary, and this is phi 2 and this is phi 1. What are okay, so and the 2 points root of EB, this 2 is root of EB, this might be root of EB comma 0, this is 0 comma root of EB, right? Two signals, and this is your region of the signal. So when something comes in favor to this R1 region, it will come across the this message point, and when something comes across this region, it will come across this region, that is message point S2. So what are R1 and R2? They are the projections of phi 1 and phi 2. And we have these all things we have said, and we found what is the probability of error for binary FSK by solving this equation, by giving the value R1 and R2 at this equation we'll get this, and for the symmetry also. And also we found that the BFK is having more probability error. Also finally we found we understood what is BFSK transmit and how it's working. When we give zeros and ones, inverter just invert the values and giving the output, and the output BFSK signal transit, and it is received using a BFSK receiver. Also we have a decision device here. Okay, we will get R1 when R1 is greater than R2, we will get 0 when R2 is greater than R1 in such conditions. Okay, so I hope the class is very clear. Okay, thank you.